Yeah, this talk is really kind of an extension of the previous one. It will talk about this paradigm in which is implemented by Scheisel, by SpinalHDL, by many others languages that you can find out now. So there is many names to this kind of paradigm. Like before we heard about hardware construction language, there is also hardware description library. I mean, whatever how you name this paradigm, this talk will try to introduce it to you and really to make you some good examples to help you in understanding how it works, the ones you can do with language like Scheisel or SpinalHDL. So yeah. So the idea is of hardware description API, I name it like this. The idea is, so you use a host programming language, a general purpose programming language like Scala, plus an hardware description API, so a library, a Scala library, for instance, with Scheisel or with SpinalHDL. You write some Scala code, which use some aspect of the hardware description API, like Scheisel or Spinal. Like, for instance, here it's saying that I want a register named reg1, which is 8-bit uint, a reg. And as I was saying that, OK, there is a signal named cond, and when reg1 is equals to 42, then it has to be true. And so when you execute this Scala code, it will, behind the scene, push some equivalent netlist into the computer memory. So when you run this code, it will create a netlist, equivalent netlist, and then it will flush it into VHDL and Verilog for synthesis, for simulations, or whatever you want. So another simple example is, OK, you want a register 2, which is also 8 bits. You say you want to initialize it to 0 when there is a reset occurring. And then when cond is true, then rex2 is assigned with value 50. And it will add corresponding logic inside the netlist. And so the basic level of abstraction, which is provided by Scheisel or SpinalHDL, is really close to the one that you are using when you are doing VHDL or Verilog. Basically, you say, I want a register, then you get it. You want a gate, you get it. You want a adder, and then you get it. You just don't have to manage process or always blocks. But it's really kind of similar. So just about the SpinalHDL hardware API, which is really close from the Scheisel one. If you want to infer hardware, you can do it through some hardware types, which are bool, bit, uint, async, bundle, and vec. All the Scala types like int, float, and this kind of things, you can use them as an elaboration tool to calculate some constant, to elaborate your design how you want, to do some for loops and things like this. But if you want to infer some hardware into the netlist, you really have to use those hardware data types. Hardware conditional statements is when and switch, for instance. Hardware operators is like to assign a signal or a register. It is, where is it? I think it's done, no more battery. So it is colon equal, behave like VHDL signal assignment or like Verilog smaller equal assignment. I know it's there. And yeah, there is so few other hardware constructs like component, in, out, area, clock domains. So SpinalHDL, as Scheisel and others, will really give you basics to describe your hardware netlist. But then on the top of this has preview side. You can really build abstraction on the top. And this talk will really focus on this aspect, building abstraction on the top and really playing between Scala and those hardware description API. So OK, just a few things before continuing, because then there will be a lot of code. Sorry about this. But OK, first, there is no logic overhead in the generated RTL, because everything is explicit. You say, I want a gate, you will get a gate. Or it's really, there is no magic. There is no black magic out of this. It will not generate broken VHDL or Verilog, because it's doing a lot of check over your netlist. You will check that you don't have latches, you have no commutator loops, you have no signal with mismatch. So it's kind of an integrated lint tool inside SpinalHDL to really make sure that your generated netlist is safe to use, safe to synthesize, safe to simulate. But as I said, this talk is not really about SpinalHDL itself. It's really about the concept. it is like really giving those key examples to help you getting the semantic of those hardware description API. Okay, so first, a really simple and stupid example. You want to write this thing with some multiplexer, really simple stuff. Okay, so you can write it a bit like you will do in VHDL and Verilog. You just don't have to write process. So here in red, sorry, it's off. Okay, here in red are all the access to the SpinalHDL API, which are adding things into the netlist. So SpinalHDL is not looking at the code you have written, but that's you. When you execute this code, when you will execute this bool function, you will say to SpinalHDL, hey, please add 2 signals, the name cond A and cond B to the netlist. So it's you. When you execute the code, you are pushing things into the netlist. So, okay, defining cond A and cond B, like really simple. Defining result as a unit of 8 bits, quite simple. Assigning result with a hardware literal with the value 0. So 0 is a Scala word. 0 is a software thing. So if you want to push a 0 value into the netlist, you have to say U to unsigned value 0 to push into the netlist. So in practice, you can just write here 0. You don't have to write this, but for the presentation, I make it explicit. And then when cond A is true, result is 42. When cond B is true, result is 255. Really simple stuff. But this slide is not about this simple way of writing things. It's about alternative ways of writing it to really understand the concept behind those hardware description API. For instance, here, it's using the fact that we are in Scala. So everything is object-oriented. If you give a signal as an argument to a function, what will happen? We will give the reference to that signal. You will not give a copy of this signal. So, OK, let's read this one. So defining cond A, cond B, and result as before, default value of result as before. And then the kind of function, like when the first argument is true, the second argument is assigned with the third argument. That's why not? And if you look at the function, it's really simple stuff. And here, for instance, you can see you are assigning the target signal given as argument. And because everything works in an object-oriented way, you will effectively assign the result signal because you give the handle to the signal, to the function. OK. Quite stupid way of doing things. There is another one now. And this is probably the main slide of this presentation. This is a key slide where basically, to infer hardware, we will build at a time a software model of what we want to create, and then we will translate it into hardware. And this unlocks a lot of possibilities. OK, so let's read it. Like, OK, defining cond A, B, result as before, default value of result as before. And then here, we're defining, we are defining a spec, so a specification, which is an array buffer. So an array buffer is really a Scala software data structure, which is an array in which you can add element on the go. So, OK, we're defining an array buffer. And then this array buffer will keep some specification elements, which is a class defined just below here. And a specification element is a class which is stored in which given condition, the target signal has to be assigned with the given source signal. So everything of this will work by reference. Then we're here adding some element into the specification. So we're adding in the spec, so plus equal to add an element in the dynamic, in the array buffer, some new spec element which describe what we want to do. So here we're already building a data model of what we want, so a software model or a database. Name it as you want, but we're really building a software structure of what you want with 2 elements. And then here, we are going into some software to translate it into hardware. Like, for each line of our specification, we will get the given value. And we will apply the condition of the given specification element to assign the target signal with the source signal. And from a SpinalHDL point of view, this will be kind of unrule. This loop will be unrule in the generated hardware. So we're really like pushing things into the netlist by using software. So, OK, now let's go in a bit more practical thing. Imagine you want to design this peripheral, which is really a simple and stupid one with a memory bus to take the control of this peripheral. And then from this peripheral, you want to take control of the signal A and B. And you do the XOR of A and B, you get the result, and you want to make this result readable by the memory bus. OK, let's do it in a funny way. So defining A and B as a register of 32 bits. result as the XOR of A and B, so really simple stuff. And then defining the memory bus has IPv3 one with this given address with this given data with. So IPv3 is something which is coming from the SpinalHDL library, not from the SpinalHDL core. So it's SpinalHDL library is really a set of things which are commonly used. So to avoid having you redefining them all the time, it's already defined for you somewhere. And there is coming the fun. OK, so let's define IPv3 MemoryMapper tool, which is a tool which is implemented on the top of SpinalHDL, a bit like diplomacy that were here before, but not for the same purpose. That's just to get the thing. And the goal of this tool is to do the memory mapping between a memory bus and some signal of your design. And then you call a function to this MemoryMapper tool to say, hey, MemoryMapper, you have to write the target signals A when the bus is doing a write access at the address 0. Or, hey, you have to write the target signal B when you do a write access on the address 4. And you have to make the source signal result readable when an access is done at address 8. And what we are doing here is we are kind of building a software model of what is our memory mapping for the peripheral. Like for a given key value, which is here the address, the integer address of our peripheral, what do we have to do? Like we have a write access on A at the address 0, we have a write access on B at the address 4, and a read access on the result at the address 8. And then, once we have built this software data model, we have to translate it into hardware by, for instance, calling a build function. And this function will translate this software model into hardware. And now I will show you how this is done behind the scene. And there you go. So you can define what is a write access. So write access is a class which do something on a target signal. Our read access is a class which do something on a source signal. Then you define a Scala class, IPv3 MemoryMapper, which has as argument the bus on which it will operate. And OK, now it's coming the funny things. Our specification now is a map. So a map is like a dictionary in Python. And a map, so the idea is you have a key value that can point you to something, a value that you store. And OK, we have a map which will link at which given address. We have to do what? So here it is an array buffer, because maybe on a given address you want to have a read and write access, so you have multiple elements to do at the same address. So it's an array buffer of things to do at a given address. And then, for instance, you implement the write function that I called just before in the previous slide, where you say to which signal should be accessible at which address in write mode, and then you add in the specification for the given address a new write access. So you are building the model. When you call this function, you will add things into the software model of your hardware. And then you need to implement the build function to translate all of this into real hardware, to infer it. So let's go to the build function. OK, so bracket open. Then some bus arbitration. You know, IPB has some, it's quite an old bus. It had some arbitration to do to understand what it wants to do. Simple stuff. And then, you know, when you map a memory bus on a peripheral, you always have a big switch statement with all it has to do. So, OK, let's push in the netlist the switch statement for the given bus address. And then let's do a software loop to iterate over each line of our specification that we built previously. And for each line, it will give you the given key value as the address and a given list of jobs of things to do for this given address. Then let's push on the netlist some is statement. So this is hardware statement to check is the bus address equals to the given key on the line I'm iterating. Then for each job of a given line, you have to iterate over all jobs that you have to do for a given address. So software loop. And then you have to identify which kind of job you have to do. So is it a write access, or is it a read access? So it is really mixing Scala software and SpinalHDL API to push hardware on the netlist. And finally, you add the logic. Like when the bus wants to do a write, you will assign the target signals with the databus. And if it's a read access, you assign the databus with the read access source signal. And this will translate this software model into the real hardware by pushing things, by mixing software and hardware and pushing things on the netlist on the go. Okay, so, and now are coming some even more funny things, software engineering, proper software engineering, where you can define abstract classes. Like previously, were defined IPv3 MemoryMapper tool. It's great, but it works only for IPv3. So maybe today you want Axelite, maybe tomorrow you want Wishbone, I don't know. So you can use all the features of Scala to elaborate your hardware. Like you can define the concept of what is a memory mapper. So okay, it's exactly as before with read-write function with a specification which is stored in it. And then you keep the build function not implemented there. You will implement it in the children classes. Like you can have one children classes to implement the IPv3 version of the memory mapper, one for the Axelite, one for the Wishbone, and there you will implement the real build function. And this is really mixing software engineering and hardware engineering. And it really makes sense because, for instance, now, imagine you define a data structure named something. So a data structure in SpinalHDL is something which extends a bundle. And let's say in our bundle we have A and B signal. Now we can add a function inside this bundle to make, for instance, this data structure readable from a given memory mapper. So you can call this function. It can be this is a data structure, but it can be a whole peripheral. And you can call a single function and give whatever memory mapping tool you want. And it will work on IPv, on Avalon, or whatever you want. So we are bus agnostic. So OK, now second part, VexRisk V. So yeah, this is our open source CPU, which were implemented with a lot of love. And it's mainly target FPGA, so yes, it's 5-stage, RISC-V 32-bit, optional multiplication, optional compressed instruction support, optional instruction cache, data cache, optional JTAG. And on AT67, for instance, it behaves quite well. Like smallest configuration can go down to 500 lookup table and up to 340 megahertz in a FPGA. And performance are quite good. I mean, kind of the same levels than microblades and Neos2. So a good soft core. But the thing is, the architecture of it, it's quite regular. It's nothing special. But the thing, it was implemented in a really weird and funny way. And by extensively using all the artifacts that I've shown you before. So, OK, there is Scala and SpinalHDL, which are really the basics to describe hardware with what we have seen. And on the top of that, there was a pipeline framework which were implemented to make this CPU. And we will get to that now. Basically, in a CPU, OK, you have stages. You have like the decode stage, execute stage, memory stage, write-back stage. Why not? Maybe you have other stage. And you always have like some really specific units, like the ELU, branch management, hazard management, register file management, the instruction decoder, whatever. And for instance, this is how we can instantiate this CPU. So you create a VexRisk V configuration, and you will fill this configuration with a lot of plugins. And these plugins are not just saying like, oh yeah, I want the integer ELU. Those plugins, each one, are the real implementation inside the CPU. If you are not happy with the integer ELU implementation plugin, you comment it out, you implement your own plugin, you feed it in, and you got your own implementation of the ELU for this CPU. So if you look at the top level of VexRisk V, it's empty. There is no logic defined in VexRisk V top level. Everything, nearly everything comes from the plugins, like hazard management, integer ELU, or debugging. Debugging with JTAG comes from one plugin. And if we look a bit how this is possible, it's made really by the framework on the top of SpinalHDL. Like one part of the framework to implement this CPU is providing kind of data flow abstraction layer to really make the plugin able to communicate to each other. So for instance, you have the program counters. Program counter, you need it to make it traveling from the decode stage, for instance, to the write-back stage. You will insert the program counter for a given from a given plugin, and the write-back, another plugin like the one which is handling interruption will need it. So you need to pipeline this program counter through the whole thing. And there is a way how it's done with this CPU. Like you define the concept of program counter as a value, a 32-bit integer value, uint value, that is stageable inside the pipeline. So here on the top, this is not a signal definition. That's the concept of a signal inside the pipeline definition. And then, for instance, in one plugin, you will say, OK, I want to insert the program counter in the decode stage with this value. And for instance, in the write-back stage, you will ask the framework to give you the input program counter value. And then what you are doing here is, again, feeding kind of software data structure inside the framework, which will be then translated into the hardware that you really need to make the right pipelining at the right place between the right guys. So another part of it is like, OK, in a CPU, you will have multiple guys which want the CPU to jump somewhere sometimes, like prediction, branch management, exception management, or maybe your own specific instruction. And it's really done in a kindly way. Like, for instance, the branch plugin will ask the program counter plugin to provide him a jump interface that will be used in the execute stage. So you have plugins kind of cooperating together. And we'll hear a bit about this in the previous, in the Chisel talk, which is talking about negotiation. So two-phase negotiation and then flushing the hardware out of the thing. And OK, last part of the presentation is about a practical example, how to add a custom instruction into this CPU by using this framework. Imagine you want to do a single instruction, multiple add, to add from two registers, byte by byte, things together and write it back to the register file. So OK, with this instruction encoding, why not? So basically, you have to implement a class, like a single instruction multiple data adds plugin, which is a plugin for VexRisk V. And you have two phases. As I said before, negotiation, which is a setup function that you have to implement, and a build phase, and a build function that you have to implement. And for instance, in the negotiation phase, which is a setup function here, you have to tell the instruction decoder how you have to decode this instruction. So for instance, where this bit pattern is detected, so here you are saying to the decoder service, so to the decoder plugin, that when this instruction is detected, then the register file has to be written. Then the instruction is using the register source 1 and register source 2, which is used by another plugin, which is managing the hazard management, which is doing the hazard management of the CPU. So you have kind of a very, very stretchy framework to add things. And then flushing the hardware out is like, OK, so in the execute stage, I want to plug a new area of logic, which is getting the input registers 1, registers 2, doing the math. And if the instruction is for us in the execute stage, then we will overwrite the register file, write data path. And that's it. So yeah, so you can add a new instruction like this. And yeah, so this is really a talk. I don't know, it's really to give you some feeling of the paradigm behind this. And just to think about it, remember that it's when you execute the Scala program that you are pushing things into the netlist. It's not the reverse, not SpinalHDL, which is looking at the code that you are doing. So you are really the master of the thing. You take the control of it. And all the fancy elaboration features like classes, like dynamic list, hash map come from Scala itself, not from SpinalHDL. And yeah, all the previous slides are just a demonstration. They are not like saying you have to use this framework because this is so cool. No, this is just to show you what is the point of SpinalHDL, what is the point of Scala, and how fancy things are made behind the scene. So that's it. Yeah, there is some links if you want to check it out further.
Thank you very much. Do we have questions? There we are.
not really a fork. It's like Quake will be a fork of Doom, maybe. You see the point is it's the same concept. It's really close, syntax is really close, but it's not the same code base at all. Sorry? No, never was.
It's a follow-up question. Do you support formal?
That's a good question. That's normal.
Yes. Do you support formal verification constructs within SpinalHDL?
I had an issue recently which asked me to add some tags about it. There is a bit of support for formal verification when you can add the formal assertions a bit. Not very much. Again, it's work in progress, a bit the same. In worst case, you can still use black box to, but it will not really be human-friendly to use black box to do formal verification. So yeah, work in progress. The issue is open. There is some progress on it.
And I thought about your second question about the timings and the clocks. Do you remember what you asked afterwards?
Yeah. So I'm mainly a FPGA guy. So I don't have a lot of knowledge about clock gating and those things which really come from the ASIC world. So I would say the same answers and the Scheisel guy.
You do know, hopefully you know about metastability in FPGAs as well.
Oh yeah, I know.
Good, thank you.
Yeah.
Okay. No more questions, then we can take them offline. Let's take the speaker again.